All right, yeah, well, thanks very much to Fang-Ting for inviting me, and thank you all for being here. So this will be a talk that's based primarily on combinatorics and analysis, just to warn you ahead of time. So based on these two papers on the archive, and some of my goals in this talk are to survey asymptotic formulas and limit shapes for unimodal sequences. I'll talk about a few consequences as well. And sort of the primary goal is to discuss some probabilistic methods for proving asymptotic formulas for partitions. And by the way, please stop me at any time if you have any questions. Just let me know. Okay, so a partition of n is a multi-set of positive integers, lambda k, that satisfy these weakly decreasing conditions, and they sum to n. And we write that in this way: lambda is a partition of n. The size of lambda will be denoted with absolute values, and then P of n will be the total number of partitions of n. So for example, there's 5 partitions of 4, and there they are. Okay, so the theory of partitions is a pretty big field in its own right, but this is a general algebra number theory talk, so I thought I'd just mention some connections to other fields. As I'm sure most of you know, one can construct irreducible representations of the symmetric group by using the Young tableau for partitions, the diagrams that correspond to partitions. A big connection to other fields is that partitions are a good source of problems in modular forms. This continues to be a very active area today. And then also partitions come up in various other algebraic structures, quiver varieties, affine Lie algebras, just to name a few. Usually one has some Q series that, well, one wants to show some Q series identity that for data for these structures, and sometimes that just amounts to proving an identity among partitions. Or maybe it can also work in reverse. You know, some strange looking partition identity is better explained via affine Lie algebras or something like that. And then another way that partitions crop up is in this new field of analytic combinatorics. So I'll talk a little bit about some of that later on. Okay, so the Young and Ferrer's diagrams for representing partitions. This is not the usual convention for doing it, but in this talk I'm going to represent parts as columns of squares. So here's a partition of 41, and every part is represented as a column of that many squares. So represented in this way, there's a very natural involution on the set of partitions of n, where you just reflect about this 45-degree diagonal, and that's called conjugation. All right, so how many partitions of n are there? So there's not an easy formula for this. So, but a useful thing to do is to answer it in terms of generating functions. So P of n is the coefficient of q to the n in this infinite product. That's easy to see. If you just start multiplying things out in this product, you'll get a q to the n exactly P of n times. And if you're a little uncomfortable with these infinite products, you can treat these Q series either formally as lying in rings of formal power series, but analytically, which is what we want to do in this talk, this geometric series can be written as 1 over 1 minus q to the k. And this is basically the Dedekind, 1 over the Dedekind eta function, which is a modular form. So I'm primarily going to be talking about asymptotic formulas in this talk. So let me briefly go over, what is meant by an asymptotic formula. So f tilde g means that the limit of their quotient tends to 1. And this limit could be some other limit. It's usually understood from the context. So here, n squared and n squared plus n are asymptotic. But it's worth pointing out that the error term here, f minus g, need not tend to 0. So here the error term is n, and that tends to infinity. So f asymptotic to g, it just means that they're good relative approximations in this quotient sense. Okay, so back to this question, how many partitions of n are there? We saw that it's the coefficients of q to the n in this product, which is essentially a modular form. And very important groundbreaking work of Hardy and Ramanujan was to use the modular properties of this function to write down an asymptotic series for p of n. That was 101 years ago. And then Rademacher later gave a convergent series for p of n. So this is what the main term in the asymptotic formula looks like. Probably pretty weird if you've never seen anything like that before, but I just want to point out that there's an exponential of root n, and we're dividing by some power of n. And that sort of pattern is a common way that these asymptotic formulas will look. This means that this growth here is sort of on the cusp of things between polynomial growth and exponential growth. So it's in between those. So this is a really remarkable fact that we have that p of n equals this convergent series. And this actually features in this film about Ramanujan's life from 2015, The Man Who Knew Infinity. So in the film is this equation here. So the number of partitions of 200, there's some 3 trillion of them, but you only need 8 terms in this convergent series to get that within the nearest integer. So pretty remarkable formula. Okay, some other asymptotic formulas. So if d of n is the number of distinct partitions of n, here the generating function will look like this. So the q to the k appears only once here because parts are distinct. Again, that's a modular form. And again, you can give a convergent series for d of n. So I'll just point out once again, there's an exponential of a square root n, and we're dividing by some power of n. All right, one more asymptotic formula. We'll say that pt of n is partitions of n where the largest part is bounded by t root n. So we have this restriction on how big parts can be. So that means that it's the coefficient in this product where we only take k up to this point. Now that's not a modular form, so we can't hope for a convergent series for this thing. But you can get the asymptotic main term. So that was proved by Zekeres, Canfield, and Romick. And I'm not going to write down these functions g and h precisely, but there's an exponential, a square root n, and you're dividing by some power of n. And okay, there's another parameter alpha that satisfies some integral equation. All right. Now these 3 authors proved this in very different ways. Zekeres gave what I would call a classical proof based on the saddle point method in complex analysis. Canfield's proof was mostly based on recurrences, and he didn't have to resort to complex analysis. And Romach's proof was probabilistic. And it's this type of proof that I'll be talking about today. So this is based on, I would call, groundbreaking work of Fristedt.
What's so special about square root of n?
That's simply where what the saddle point equation gives you, which I'll talk about saddle points later on in the talk, but square root n is just what the it has to do with the location of the saddle point and the nature of the singularity of this product at 1.
Okay.
Yeah. Okay. So here is my asymptotic formula. It's the same thing as on the previous slide, except parts are distinct. So dt of n is distinct parts partitions. Again, abounds on the largest part. So that's coefficient of q to the n in this product. And okay, for posterity's sake, I wrote down the whole thing, but I just want to call your attention to the fact that there's an exponential of root n dividing by some power of n. But the difference here is that there is this oscillatory term here. So these curly braces represent fractional part. So this thing actually oscillates as n tends to infinity. So it's different from what we see on the last slide. And I gave a proof motivated by probability theory. And okay, I didn't just want to prove this out of the blue. The motivation here was that I needed this asymptotic formula to study limit shapes for unimodal sequences. And yeah, I was kind of surprised to not see this anywhere in the literature, but it doesn't appear there. And the primary points of proving it is to demonstrate these probabilistic methods. So now I'm going to turn to limit shapes of unimodal sequences. So are there any questions up to this point about anything? Okay. All right, so limit shapes. What are the typical shapes of diagrams of partitions of n? It's like if you choose a big number n and you look at all the diagrams, what shapes would you see? What are some common shapes? So here is a density plot of all the partitions of 300. So here in this diagram, a square is shaded according to how often that square occurs in partitions of 300. And as you can see, it appears that the majority of diagrams of partitions of 300 are close to this blue curve. So it appears that there should be one limit shape. And so I don't know about you, but I mean, the first time I learned about this, I was very surprised. And I guess, you know, the more you learn about something, the more, you know, the excitement wears off a little bit, but you know, it's quite a striking fact that there's one limit shape. Okay, so to state this a little bit more precisely, we'll say phi tilde of lambda is the renormalized shape where we rescale by 1 over root n. That ensures that the total area underneath the diagram is 1, and once we do that, we can now talk about shapes as n tends to infinity, right?
So what's on the x and y axis again?
I mean, it's just it's just the diagram. So, you know, here this diagram would be a diagram for a partition 5, 5, 4, 3, 1, 1.
Okay. Are you saying that most diagrams will be scattered around this curve as n goes to infinity or something like that?
Yeah, so I'll show you the precise statement on the next slide. Okay, so yeah, this is the precise statement here. So this curve, the blue curve on the previous slide, is described by this equation. And if n epsilon is an epsilon neighborhood of this curve, this is the conjectured by several people. Temperley actually, for statistical physics reasons, and Verschick made this conjecture using Fristedt's probabilistic machinery. So this is basically what the conjecture states, that the proportion of renormalized shapes that are within epsilon of this curve tends to 1, as n tends to infinity. So as n tends to infinity, almost all diagrams are within epsilon of this limit shape. So as you can see, this curve is symmetric in x and y, and it should be symmetric in x and y because we have this conjugation, this reflection, 45-degree reflection of diagrams. So if there's going to be a limit shape, it needs to respect that symmetry, and it does. So this was proved in '98. So Dimbo, Verschick, and Zaituni proved a much stronger large deviation principle, and their proof was based on some probability. And I also just want to point out that a limit shape is also known for distinct parts partitions, looks like this. And yeah, limit shapes for many types of partitions are pretty well known. Okay. So the question I wanted to ask is, are there limit shapes for unimodal sequences? So what is a unimodal sequence? A unimodal sequence, lambda of size n, is a sequence of positive integers satisfying these equalities. So, and then parts summing to n. So for partitions, parts have to be weakly decreasing. For unimodal sequences, they can increase weakly and decrease weakly. So we'll refer to lambda p, this part in the middle, and any other parts of this size, we'll call those peaks. Now you might think, well, I mean, that just looks like pairs of partitions to me, but that's actually not correct. So there are strictly fewer unimodal sequences than there are pairs of partitions. So we'll see that on the next slide. But anyway, there are 8 unimodal sequences of size 4. So here they are. For example, you can take this partition 2 plus 1 plus 1, and it's counted 3 times as a unimodal sequence. So, you know, one of the sort of ongoing projects in the theory of partitions is to see, you know, how much from partitions we can apply to unimodal sequences, and it turns out to be generally quite difficult to transfer some things. So unimodal sequences are, because there isn't a well-defined ordering on the parts, unimodal sequences tend to be a little bit more difficult. So because of peaks, unimodal sequences are not this double partitions, they're not pairs of partitions. So this generating function is not equal to this infinite product squared. You have to multiply by this sparse series that accounts for the peaks. So this infinite product is basically a modular form, and this is what we call a false theta function. And I just want to point out that an asymptotic main term for u of n, it goes back to the 50s. Again, you have an exponential of root n. dividing by some power of n. But we had nothing anywhere close to a convergent series for U of n until last year, when Ringman-Nazaroglu gave a convergent series for U of n, really as a consequence of putting this false theta function into a modular framework. Any questions up to this point? I feel like I'm going kind of fast. Okay. All right, so limit shapes for unimodal sequences. I'm going to describe limit shapes for these three types of unimodal sequence. Unrestricted, which is what I've already defined. Strongly unimodal sequences where we have strict inequalities on the left and the right. And then semi-strict, strict inequalities on the left side, say. So again, we'll renormalize these diagrams by dividing by 1 over root n when the size is n. And you want to see if there is a single limit shape in each of these three cases. Okay, so let's recall the limit shapes for partitions, unrestricted and partitions into distinct parts. They look like this. So, you know, unimodal sequences are not pairs of partitions, but maybe heuristically we can think of them that way, at least heuristically. So one would conjecture that limit shapes for unimodal sequences would look like this, right? And okay, semi-strict unimodal sequences, okay, you'd expect the left to look like this and the right to look like that. But the question mark is here because it's not clear what the scaling should be. So the area breakdown, total area underneath the curve has to be 1. Is it going to be 1/2, 1/2 on the left and the right? Is it going to be 1/4, 3/4? What's the breakdown going to be? Okay. So here are the results. Indeed, we do get the expected limit shape for unrestricted unimodal sequences. So that's what it is. Each side of this shape is the limit shape for partitions, scaled down so that the area here is 1/2. So, you know, if you take this and put x and y on the same side, you get the equation that I've already showed you. We also get the expected limit shape for strongly unimodal sequences. And for semi-strict, the limit shape looks like this, and the left area is 1/3, and the right area is 2/3 here. Okay. So how do we interpret these limit shape results? So a limit shape is basically a 0-1 law for the medium-sized parts. So the parts that are on the order of root n. So for example, you could say something like this. As n tends to infinity, the number of parts of almost all strongly unimodal sequences of size n lies in this very tight interval around root n times this constant. So, I mean, there are many similar statements you could make like this. But it's worth pointing out that the limit shapes say very little about the small and the large parts of a partition or unimodal sequence. So small and large in reference to this root n. Okay, I think I'm going to skip this. Okay, so let me give you just one consequence of these limit shapes. So here's a question: are there limit shapes for overpartitions? So an overpartition is sort of similar to a partition. These were introduced in 2004 by Corteil and Lovejoy to explain some Q-series identities. And, you know, their theory parallels that of partitions, and, you know, a rough measure of how much people care about this is that, you know, their paper has a lot of citations on MathSciNet. So what is an overpartition? An overpartition is a partition where the last occurrence of a part may or may not be marked. So here are the overpartitions of 4. So for example, this partition 2 plus 1 plus 1, I'm allowed to overmark the 2 or this first or this last 1, I mean. So this 2 plus 1 plus 1, it appears 4 times here. So over P of 4 is 14. There's 14 things here. Okay, now what the heck does this have to do with unimodal sequences? Well, it has to do with bijections. So DeSalvo and Pack recently showed that geometrically nice bijections among partitions mean that you can transfer the limit shapes. So this picture is showing you on the right-hand side a bijection between certain types of partitions. Here, these are partitions that are symmetric about the 45-degree diagonal. And the set of partitions over here is a partition into distinct odd parts. Okay, so there's a very simple bijection here. And that means that, I mean, you can basically do the same procedure on the limit shapes themselves and recover a limit shape for this other type of partition, right? Okay, so it turns out that overpartitions are connected to semi-strict unimodal sequences. So if SSN, SS of n is the semi-strict unimodal sequences of size n, then it turns out that over P of n is SS of n plus SS of n plus 1. And there's a very simple bijective proof here. So if I start with an overpartition with a single marked largest part, so you hear these yellow boxes mean I'm marking that part. In that case, you just shift the marked parts over to the left side. And then in the second case, if there's at least one unmarked largest part, then put a box above him and then shift all the marked parts over to the left side, and you get a semi-strict unimodal sequence of size n plus 1. So, you know, we're going to have strict inequalities on the left side because marked parts are distinct. Can mark a part at most once. Okay, so the bijection is, you know, you basically just shift stuff. I mean, if we start, okay, so starting on the right-hand side, the bijection is just shift stuff to the right. So, you know, inspired by DeSalvo and Pack's work, I showed that we can transfer the limit shape from semi-strict unimodal sequences to overpartitions by just basically adding the horizontal components across here. So here is your limit shape for overpartitions, right? And there's the formula. So just like partitions, overpartitions have a conjugation symmetry, a reflection about the 45-degree diagonal. So this should be symmetric in X and Y, and indeed it is. Okay, so that's basically all I wanted to say about limit shapes. I'm now going to get into some of the probabilistic proofs of asymptotic formulas. Are there any questions at this point? Okay. Oh yeah, and I did have this one slide. So here's the comparison between limit shapes for partitions and overpartitions. They're very similar looking shapes. And I don't really understand why they're so similar. So, you know, is there a more direct combinatorial explanation for this difference we see? And more generally, how should we alter the definition of partitions to achieve certain effects in the limit shape? So, I mean, I know this last question is basically asking, well, limit shapes for different types of partitions, but I think phrased in this way, I'm not sure that this question has been asked, has been phrased in exactly this way before. So, okay. So a probabilistic proof of the asymptotic formula for this thing. Okay. So first, let me just overview the classical approach to these sorts of asymptotics. So this is, you know, just really just a picture for how this works. So this is the circle method and the saddle point method. So for example, the inverse factorial here, 1 over n factorial, that's the coefficients of q to the n in the exponential function. So by Cauchy's theorem and complex analysis, it's 1 over 2 pi I times the integral of e to the q over q to the n plus 1 dq over a circle C. Now, we can choose to circle C, encircling the origin, however we want. And here's how we do it. So picture says 1,000 words. There are 1,000 words to say about this, I guess, but here's what this looks like. So here's the modulus of the integrands for n equals 8. So we can see the singularity at q equals 0 of the integrands, and the, well, singularity in quotations of the exponential function at infinity. So it's convenient to choose your circle to trace through this saddle point here. And so as n tends to infinity, asymptotically, the portion around the saddle point is going to dominate, and this other stuff here is going to be negligible. So the main term here asymptotically comes from around the saddle point. And choosing the saddle point is really key to being able to evaluate this integral. So it's key that the derivative vanishes there to evaluating the integral. So if you do that, in this case, you get Stirling's formula for the factorial function. Okay. Okay, so now the probabilistic method. So in 93, Fristedt introduced a new probabilistic framework to study partitions. So some notation: if Pn is the uniform probability on partitions of n, so Pn of lambda is 1 over the total number of partitions. So we care about, you know, the distribution of statistics for partitions under this uniform probability measure. So Fristedt found, so many people had found distributions of statistics before Fristedt, but he went sort of way beyond the work preceding him and found joint distributions for example, the smallest Tn parts, the largest Tn parts, etc., under P of n. And so the idea, this is called Fristedt's conditioning device. So the key idea is to treat capital N, the size of a partition, as a random variable. Then the uniform probability measure is equal to QQ, this other probability measure, on all partitions conditioned on capital N equals N. And so this is really a family of probability measures depending on this parameter little q, but it's better because it's easier to work out these distributions under QQ. And then Fristedt gave a way of transferring such results back to uniform measure. Okay, so I'm going to get more concrete with this in my particular case. So remember, the goal is to find an asymptotic formula for dt of n. So that's the coefficients of q to the n in this generating function here. Okay, so here's how we define the probability measures. So for a parameter in 0, 1, define the probability of lambda to be q to the size of lambda divided by the generating function. Now, is that a probability measure? Well, yeah, if you add that up over all partitions lambda, you get, generating function over generating function, which is 1. This is a probability measure. We'll introduce some random variables, xk's, which tell you the number of k's in lambda. So since we're dealing with distinct parts partitions, xk is either 0 or 1. So for example, x3 of this partition is 1 because there's 1, 3. And x4 of this partition is 0 because there's no 4s. And then also we'll let capital N be the sum of k times xk. So if you add up k times the number of times it appears, that gives you the size of a partition. So n of this partition is 10. Okay, so here's some easy facts about this setup. Here, the xk's are independent under QQ. Now, that models sort of heuristically what we expect for the small parts in a partition, if you think about it. So for example, the number of 2s and 3s in partitions of 100 aren't independent. But, if I make 100 into 1,000 and, as the number gets bigger and bigger, you expect the number of 2s and 3s, expect those to become closer and closer to independent. So at least this, models what we expect to happen for small parts. Now, the probability that capital N equals N, well, you just add up q to the n times the reciprocal of the generating function, you add that up dt of n times. So here's this equation. But now we have an equation for this thing that we're trying to find an asymptotic formula for, right? The goal is to figure out the growth of this little dt of n. Okay, so there's a particular choice of the parameter q that is relevant here. So one has this trivial inequality for any positive number q. This is a trivial inequality, right? The nth coefficient is definitely less than this entire generating function here, right? However, this inequality is not too far off from an equality in a certain sense. And there's a certain choice of q that minimizes that. Now, if you minimize that by this equation, you maximize this probability. And heuristically, that's what you want to do. You want to, if we're going to use this QQ to study the uniform probability measure, we should maximize this probability that capital N equals N. So in the familiar language of the way this thing works, we're saying that the saddle point equation is the same as saying that the expectation of N equals N, which is like to maximize the probability that capital N equals N, you want to make the expectation of capital N N. So yeah, so these things are actually the same thing. Okay. But capital N is a sum of independent random variables. So you expect some sort of central limit theorem to hold, and that turns out to be the case. So, I mean, you have to prove that, and it's a little tricky, but you can prove that this capital N satisfies this central limit theorem here. So now we can give a heuristic at least for what this probability has to be. Okay, so the probability that capital N equals N, capital N takes integer values, so these two things are equal. Now, you cannot at all pass from the central limit theorem to this local limit here. In general, you can't do that, but it does turn out to give you the right thing in the end. So this heuristic, which tells you this probability, actually gives you the correct thing. So we have a heuristic derivation for the way this asymptotic formula should look. So this is roughly what we're doing. So this flipping around what I had, dt of n equals this probability times q to the minus n times the generating function. So with this choice of q, one uses, okay, Euler-Maclaurin summation to analyze this, and then Fourier inversion of the characteristic function for capital N is how you prove the heuristic I had on the previous slide, and essentially that leads to these portions of the asymptotic formula. Okay, so if you didn't get a lot of that, basically what I'm saying is that the probabilistic way of thinking more or less predicts how this asymptotic formula should look. Okay, so you can take this probabilistic framework for partitions and actually extend it to other combinatorial structures as well. So Fristedt was, one of the first to develop these ideas for partitions, but then, these four authors developed these things in general. So Duchamp, Flageolet, Bouchard, and Schaefer gave Boltzmann models for general combinatorial structures, and it works basically the same way. So if you have classes of objects of size n, and C is all the objects put together, then in the same way as before, you can study the uniform probability measure using the Boltzmann model, so-called Boltzmann model, where just as before, the probability of gamma is defined to be q to the size of gamma over the total generating function. So essentially what we're doing there is allowing the size to be a random variable rather than restricting to objects of size little n. If you allow the size to be a random variable, that's helpful. And so one of the things they showed is that this leads to faster sampling algorithms for these combinatorial structures.
Just one question, Walter. Yeah. What role does Q play in all this? It seems to disappear in the end from your formulas.
So Q, yeah, so there's a particular choice of Q that's useful, and it comes from, okay, so this expectation of capital N equals N, that equation, you can take this as the definition of little q.
Oh, I see. You found a special q. Yeah, but then there's a beta. Okay. Well, anyway.
Okay. Well, the beta and the q, are the same thing. I mean, you can take this as the definition of beta. As like if you define q, you define beta as well.
Okay, I guess I don't know enough statistical mechanics to know what's going on here. But anyway, go on.
Okay. No, yeah. That's a good question, but yeah, okay. Okay, so yeah, the Boltzmann model is useful for studying partitions, as Fristedt showed. So you might wonder if we can do the same thing for unimodal sequences. But really, the key thing about partitions in so many ways is that its generating function is an infinite product. And as we saw, the generating function for unimodal sequences is not an infinite product. And basically that means, maybe this is too strong a statement, but you know, the amount that I've tried to use it, I haven't found the Boltzmann model to be useful. So I think a different approach is needed if we're going to go as far with unimodal sequences as we can go with partitions. Okay, and I guess I'll end on this slide. So I've talked a lot about different limit shapes. So this is what the limit shapes for these partitions, distinct partitions of n with a bound t root n on the largest part. This is what these limit shapes apparently look like, and I don't think it would be too difficult to prove this using the known techniques. So yeah, I mean, here are what these look like for different values of t. Kind of a curious thing to me is that the concavity of these curves switches at t equals 2. So, you know, do we have an explanation for that? I don't know. Okay, well, yeah, I'll stop there. Thank you very much for listening.
Thank you. And any questions or comments?
Just one little comment again, Walter. When you wrote that Q as e to the minus beta over root n, you know, in statistical mechanics, what you have is e to the minus energy. You know, usually there, this is just an analogy, right? When you actually do statistical mechanics, what you have in your partition function are exact. See, this thing here becomes e to the minus energy over Planck's constant or some nonsense like that. Okay.
Mm-hmm.
No idea what that could possibly mean, but since you're doing statistical mechanics, has anybody taken a look at the entropy?
I don't know. I don't know hardly anything about statistical mechanics, so I couldn't tell you. Yeah, certainly there's. So really, the reason this is e to the minus a constant times root n comes from the growth of the partition function at comes from the nature of the singularity at q equals 1. But I don't know about statistical mechanics. So,
well, my belief is that there must be some interesting connections to the subject.
Yeah, definitely.
Walter, at the beginning, you mentioned about the asymptotic curve for the partition function.
Uh-huh.
So has that been proved? You only mentioned that as a conjecture.
No, I said quickly here it's been proved, yeah. Okay. So Dembo, Vershik, and Zaituni, so they proved a much stronger large deviation principle here, but there's also sort of more elementary proofs of this as well that are known.
So it's similar kind of ideas that you are using?
For unimodal sequences, essentially, I mean, yes, it's sort of like you work out the limit shapes for the left and right, but you also have to be able to put those together. So that requires a bit of work to be able to put those together. But certainly heavily influenced by these proofs. Yeah.
Yeah, I think one of your picture kind of combined two different color kind of curve.
Oh yeah, that was partitions and overpartitions. So this one?
Yeah. So they actually, are their asymptotic behavior the same, or?
No, they're different curves. The red and the blue curve are different curves. They're different limit shapes, but they're very similar looking.
Yeah, indeed. All
Yeah.
right, thank you.
But yeah, I mean, I don't really understand why they're different, you know, unless I go through this transfer from semi-strict to unimodal sequences. I mean, I don't understand why combinatorially they would be similar, you know, or they would be different in this way. So
Maybe because of the marking in the end, that maybe in comparison, that how many you can mark compared to overall how many parts.
yeah. So the marking, you could say something about the number of marked parts. If you go through, so if you go through this right here, so remember the 1/3, 2/3 area breakdown? Mm-hmm. So 1/3 of the area is over here. That's telling you that 1/3 of the mass of parts is marked, usually. Something like that.
All right, thank you.
Yep.
Any other questions or comments? Okay, so if no, let's thanks Orta again.